Deep breath, because it's our last class. We are 3 proofs away from being done. I am blatantly stealing this idea for a last class time from Jeff, who has taught INTD301 for a long time, and he has always made this his last class, and I agree that it is a great way to end a semester together. We do some really serious mathematics that is actually quite relevant to us. 3 numbers today that are irrational. Let's start with the easiest to prove. This is the only one that I suspect you came into our course knowing why it is irrational. Maybe you proved it for the square root of 2 or the square root of 5 or the square root of 7, and it really doesn't matter. The proof goes something like this. Suppose that the square root of 3 is rational. And we do this telling the folks at home who are going to watch this video just because we do this, we are pretending, we are setting up a proof by contradiction. We are setting this up. We're going to suppose that the square root of 3 is rational. Math is going to break somewhere down here. And when math breaks somewhere down here, we're going to go back and say, no, algebra was fine, number 3 was fine, it was all fine, it was all fine. This is where it went wrong. So we're going to suppose that the square root of 3 is irrational, knowing that something's going to go wrong, and when that something goes wrong, we're going to say, okay, this was wrong, that's right. Then the square root of 3 is p over q, where p and q are positive integers, and q is not 0, and p over q is in lowest terms. We set that up. We set it up. The square root of 3 is clearly a positive number, so p and q are positive integers. Q is not 0 because it can't be, because rational numbers don't allow the denominator to be 0. And we set it up so that p over q is in lowest terms. This is the key. Then cross multiply and square. That has to be true. Cross multiply and square. 3q squared is p squared. So now, what goes wrong? These two numbers are equal. This number has a 3 in its prime factorization. So if this number has a 3 in its prime factorization, this number must have a 3 in its prime factorization. This implies p squared is a multiple of 3. So 3 divides p. How do we know? Because this is just 2 factors of p, right? So there's all the factors of p and then all the factors of p again. There's a 3 somewhere in there, so it's either in the first set of factors of p or it's in the second set of factors of p. Thus, p is 3k for some positive integer k. And then we substitute. 3q squared is 3k quantity squared, and that means that q squared is 3k squared. And then we run into the same trouble on the other side. These are 2 numbers that are equal. There's a 3 in the prime factorization of this number, which means there's a 3 in the prime factorization of this number. So this implies that q squared is a multiple of 3. So q is a multiple of 3. and thus Q is equal to 3m for some m, for some m in the positive integers. Well, what goes wrong? What goes wrong is this goes wrong. The GCD of P and Q is supposed to be 1, and yet here we go. So what? Therefore, the GCD of P and Q is at least 3, which is greater than 1. So the GCD of P and Q is at least 3, but the GCD of P and Q has to be 1. This is a contradiction. So the square root of 3 is irrational. Right? And this is the sort of thing that you can work through with teenagers. We work through this in Math 140 with elementary educators. This is most absolutely the sort of thing you can do with teenagers. Teenagers understand prime factorizations. So this is a nice refresher of something you learned in Introduction to Proof. And it's a nice thing to have handy to work with teenagers on so that you know that there are such things as irrational numbers. Not everything is a fraction. 1 down, 2 to go, friends.